All right, let's get started. I'll give you a recap of the things we talked about yesterday as we all wake up in this morning. So we talked about various concepts in effective field theory that are pretty important, so I'll just review some of them. There's this is important even in quantum field theory, this difference between regularization of the theory and renormalization of the couplings and operators in the theory. Those are two distinct things. We can make two different choices for those two different things. And what the couplings end up depending on is our choice of the renormalization scheme, not the choice of the regulator. Of course, some regulators make it easier to define some schemes, so they're not completely independent, but separating those two concepts in your mind is actually very important. We talked about renormalization group equations. So we said when we do renormalization, we have a bare coefficient, we switch to a normalized coefficient, that involves some z. I wrote it as a matrix because in general, the operators in the effective theory, there may be more than one and they may mix with each other under this renormalization procedure. This z then actually defines for us the flow of those operators, their renormalization group equation. And so we derive this little equation by noting that the bare coefficients don't depend on the renormalization scale, say the ms bar scale mu. And that leads to an equation that relates the mu dependence of the z, given in this square bracket, which defines the anomalous dimension matrix gamma, to the mu dependence of the renormalized coupling. And that is going to let us sum large logs in the theory. It's going to let us flow from one point in the theory, one renormalization scale, some high scale to some low scale, or vice versa. You can reverse it. And that's very important for thinking about what are the right couplings at a certain scale to be used to make predictions, because sometimes they change by factors of 2. So it's not necessarily small effects, because you're adding up a bunch of, each little step might be small, but you're adding up a whole bunch of small steps. The other concept that I keep mentioning that we haven't yet done an example, but we'll do one today, is this concept of matching, where I remind you that what we're doing with matching is fixing the ultraviolet of theory 2. The ultraviolet was never sort of the design of theory 2 was to get the infrared physics right. Theory 1 has a better description of the ultraviolet, and we can correct theory 2 to incorporate the information that we know about from theory 1 through this procedure of matching. And we do it by equating renormalized S matrix elements. So we'll see an example of both of these things today. And that's why I introduced heavy quark effective theory, because I want to use it for my example. So let me remind you what we did at the end of last lecture. So I said that this heavy quark effective theory, or effective theory for static sources, is a nice theory for heavy mesons in QCD, or for static color sources or static charge sources of any type, depending on what group you're in. So if we're in SU3 color here, then we're in the heavy quark effective theory. We have this effective theory field, QV. It only contains the particle, the heavy quark, not the antiparticle. And we derive this equation two different ways. We derived it by expanding the propagators and vertices of the theory, and then just sort of writing this down, saying, oh, this gives the right Feynman rules. And then we derived it in a direct manner, starting with the QCD Lagrangian, realizing that we had to make a particular field redefinition before we started to expand in order to sort of identify what this QV field is doing, because this QV field, remember, is describing fluctuations about the mass. So we've re-zeroed our energy so that we're describing fluctuations with this being the zero. There's no mass in this formula, but the energies that we're measuring with this formula are relative to that mass. Okay, now there's a little phase that was important. So I want to just start today's lecture, a few more comments about this theory, and then we'll start doing some calculations in it. Yeah, let's see. So I'll make a list. So when we derived this, either way that we derived it, it was a tree-level derivation. Okay, we didn't do any loops, we didn't do any path integral. When we did the propagators and vertices, we just wrote down a single propagator, single vertex. We didn't have any loop diagram, right? And when I did the manipulation with the Lagrangian and the field redefinition, Again, there was nothing in there that could encode loops. So the derivation was tree level. Sorry about that. But it's actually, the Lagrangian that we derived is actually true for loops as well. And you could be more fancy and look at the path integral. But the basic reason that it survives loop corrections and it doesn't, for example, get any coefficient is because, well, it's a single operator, it's the kinetic term, and we're always free to normalize the kinetic term, and this is a nice way of normalizing it, so that's a freedom. There should be, we can just choose there to be no Wilson coefficient. And then there's two operators here, v dot partial and v dot a, but those are connected by gauge invariance. Okay, so it's valid at loop level. I said last time that we've integrated out the antiparticle. So there's no pair creation in this theory. Last time we had a Lagrangian, so we had a QCD Lagrangian that we wrote in terms of funny variables, QV and BV. And then I said BV is very heavy. We saw that explicitly in that Lagrangian it had a mass of 2m. So like this was sort of mass 0, this was mass 2m, and that it was about this re-zeroing of the theory around the heavy quark mass. And so this BV field in that Lagrangian, for example, you could, if you go back to it, you could have interactions like this in QCD, where sort of, you know, the propagator contains both particles and antiparticles. If we go back to this Lagrangian, I could insert the operator that changes from QV to BV and have some kind of diagram like this. But this BV is now a propagator in this diagram, even if it has external QV fields. And this is going to cost me a 1 over m because of the fact that this BV field has a large mass. So integrating out the BV is real, and effects from fluctuating into a BV, i.e. the antiparticle, are suppressed. They're 1 over m corrections. Okay, so likewise, if you sort of thought about a gluon fluctuating into a QQ bar pair, that's just not part of the theory. This theory just only has the particle. So here's the pair creation. Well, remember back at the first lecture, I told you that sometimes there's emergent symmetries in effective field theories. And this is an example. There's something called heavy quark spin flavor symmetry in this Lagrangian. So this QV field, if we consider bottom and charm quarks, can be organized as a column vector where charm with spin up or spin down and bottom with spin up or spin down are put into a column. And it's the same Lagrangian. So I can do a U4 symmetry, and this Lagrangian remains unchanged. And because there's spin and flavor in this column vector, it's a spin flavor symmetry. Okay, that wasn't apparent in QCD, because in QCD, so we can compare, we'd have charm, ID slash minus M charm, and we'd have bottom, ID slash minus M bottom. And the charm mass and the bottom mass are different. There's no symmetry between the charm and bottom here. And the D slash means that there's no spin symmetry either. Okay, so it's only when I take the limit that MV and M charm go to infinity that they sort of become equatable, so to speak. And then I have this symmetry. So it's emergent in that sense. And it's very useful, actually, for making predictions because we can relate matrix elements of operators. We can even normalize some form factors. So it's very powerful. I'm not going to talk much about it. But I just wanted to point that out to you. There was this v that showed up, and remember it was a velocity, v. It was kind of an auxiliary vector. It squared to 1. That was the only thing we had to impose on it. And it was kind of demanded of us in order to separate the momenta into a big part, with proportional to the mass, and a small part that was describing the fluctuations about the mass shell. That's where it came from. And you see that it's explicitly here, v dot d. So it made sense to put a subscript v to remind ourselves that this theory somehow we had to specify a v in order to set it up. And you can think of v as we made a choice of some frame when we expanded and got this Lagrangian. The rest frame would be very natural. Let the heavy quark sit at the origin. That would be a very natural choice of frame. We don't have to pick that frame. And we could have v be moving, and then everything is equally good. But we had to do something. And so there's a breaking, if you like, of Lorentz symmetry by the choice of this one auxiliary vector. It's broken in a very specific way, and the restoration of Lorentz symmetry in this theory actually goes under the name of reparametrization invariance, which I'm not going to have time to talk about. But there's a reparametrization symmetry associated to changes of v, and the theory actually respects that symmetry. And the thing that's not subtle about it is that it actually connects operators at different orders in the power counting, because you've essentially got an expansion of Lorentz symmetry in your 1 over m. So there's lots of interesting stuff associated to that. It is something that I cover in my online course, so if you want to learn more about it, you could look at that. But for our purposes, the point is that there's this v, and it's just fixed. We pick it appropriate to the process. We'll see an example of that today. And it's conserved by the interaction, so it doesn't have to change when I have gluons, et cetera, because their low energy gluons aren't changing the v. So it's just there, and that's okay. See if I said a lot of words, so let me pause. Yep. Sorry, can you speak up? Yeah, so there is a U1 inside, right. So there's a U1 inside the U4. That would be just particle number. Maybe I'll answer your question, but maybe you can ask it again if I don't. So this symmetry is apparent in this Lagrangian, not apparent in this Lagrangian. The fact that it's not in QCD means that at some point it's going to be broken. Yep. And what's going to happen is if I go to subleading power, the next order down, both the symmetries are broken. Both the spin and the flavor get broken at that point. But at the leading power, it's there. No, you still have light degrees of freedom. Very good point. So the Lagrangian, if I'm honest, or if I'm more complete, or if I don't miss anything, is this plus LQCD for all the light degrees of freedom. So all the quarks and gluons are just the usual QCD Lagrangian for up, down, strange, everything lighter, as well as for the gluons. It's just the usual QCD Lagrangian. So it's only the heavy quark that I've done something to, the charm in the bottom. Yeah, good question. Thanks for asking it. So I want to make this connection to the static sources. So let me just spend a moment to do that. If we go to the rest frame, so we pick v to be 1, 0 vector, then this LHQET, 0. I'll just keep leaving this part off because it doesn't change from QCD, is just a time derivative, well, a time covariant derivative, like that. And we can think about, naturally this governing time evolution of a heavy quark that just sits at the origin, propagates forward in time, and acts as a source of gluons through the D. So it's a static color source. If this is time moving up, it just, propagates forward in time, and it can emit gluons, which is, in this frame, A0 gluons as it propagates. Or usually we denote time this way, so equally well I could have done that. This is some propagator, these are some gluons, I produce it somewhere maybe, and then that's what it's doing. And so we could either talk about it like a heavy particle that was so heavy that it was fixed, or we could talk about it just as a source. Maybe we're just interested in studying some sources, we want to probe some theory. This is how you could add a term to a theory to probe some charge of the theory with an external source term. This is good for that as well. Right. Source term to probe, in this case, color, but could be some other group if we so choose, to probe the charges in the theory. Okay, so we're going to use this theory to do something. I'm going to have in mind two applications. So heavy quark could decay to a light quark, an electron and a neutrino. So this is a B to U transition, VUB, transition from a down-type quark B to an up-type quark U. That happens not through a quark, that happens through a quark level process, but we observe it through a hadronic level process, which is, for example, a B-bar meson, which has the B quark in it for historical reasons, changing into a pion. So both of these pick up an antiquark and become these mesons. And we can measure that process and look for the CKM matrix element VUB, Standard Model parameter. So in QCD, or in electroweak theory, this is just given by a current. It would be a left-handed current, right? Because it's a weak interaction. But only the vector part of that left-handed current actually matters for this process, because this is a scalar, this is a scalar. And for scalar to go to scalar, we don't need the axial part, but just because of the quantum numbers. So we can actually just study the vector current here, U bar gamma mu B for this particular process. If we had a rho meson here, then we would need the axial part, axial vector. So this current in QCD, let's call it QCD, comes from the full Standard Model. This current in QCD, I didn't write the W boson down. That's external. The electron neutrino, that's external. We know how to do the calculation of that part. So let's focus on the QCD part. So the QCD part is this current. And I'm going to have to think about what is this current going to become when I go over to the heavy quark effective theory. So there's going to be some change. Well, we can kind of guess what it's going to be. So let me write J for HQET. We're only going to care about the lowest order. So I put a 0 on it for the lowest order. Well, what would we guess? We would say, oh, it's the same thing. I just take this B, and I can replace it by my QV field, which contains the B. And that's a reasonable guess, and it's also the right answer. Up to the fact that we might get more than one operator. So can anyone tell me what other type of operator I might get? There's one more. Yeah. Yep. So V is a vector. It can replace the gamma. And so indeed, there's a second operator that has a V mu in it instead of the gamma. And you might object that, don't those have aren't connecting lefts and rights? And you would be correct that they are connecting lefts and rights differently. This is connecting left to left, and this is connecting left and right because it's a scalar operator. But this is a heavy quark. And so, as you saw in Fabio's lecture, with the mass of the heavy particle can switch left to right. and we're integrating out the mass of the heavy particle, so there's no problem with left goes to right. The mass of the heavy quark can just do that. And so we have both of these operators. All right, well, let's have a second example, just to make things slightly more interesting. So another example we could have is a transition between two heavy quarks. So B goes to C, E nu bar. This would be something that you can measure with B bar goes to D, E nu bar. Could be mu as well, of course. Often people talk at the same time about excited D, called the D star. So that's another option. D is a spin 0, D star is a spin 1. Those are actually related by heavy quark symmetry. They end up in the same doublet in heavy quark symmetry. And so people talk about these things at the same time. In this case, we can go through the same exercise. We have C bar, gamma mu. If I include the D star, which is the spin 1, I need to note that this had both a vector and an axial vector part, so I put in my 1 minus gamma 5 over 2. So this is the current in QCD from the W boson. I need the full left-handed current here. And then I can do the same exercise we did up there. And I'm not fancy enough to have two different notations, so I'll call it the same thing. We'll have to remember which case we're studying. So I'll call it J mu HQET 0 again. We're either in the first case or the second case, same notation. And we can just enumerate operators again. Okay, if we wanted to keep track of the flavor, we could use Q's here, but let me start by using flavors just to sort of denote which part of the Q we're looking at. You know, it has all these components. We're looking at some subcomponent transition here. In the HQET, we should think of the gamma 5 and the 1 parts of the operator as two different operators. So I'm being a little lazy, and I put a curly bracket, 1 comma gamma 5, either or. So these are two operators. I have the BV, it changes to a C. In this transition from that I'm doing here, where B changes to C, and there's a W boson and an electron neutrino. This is the current, right? This transition from B to C that happens through this external momentum transfer into the electron neutrino, it doesn't need to conserve V. So I can have V for the B, and for this charm, I can have some other V, V prime, and I actually need to do that in order to calculate this process. And so that's why I put a different subscript on my charm quark here. I put a V prime. I'll say more about that in a minute. Let's try to complete the operator basis. So we have this, but we could do the same game we did up here. So we could have CV prime. The gamma could be a V. BV. Or it could be a V prime. It's another option now. So there's 6 different operators. There was 2 for the first case. There's 6 for the second case. Okay, let me say a few more words about the V and the V prime. V for the B, V prime for the charm. Let's think about the kinematics of this process at lowest order in our heavy quark expansion. Well, at lowest order in the heavy quark expansion, for the process that we're talking about here, let me just do this first one. I would just say the following. I'd say the kinematics of the hadronic process are given by the mass of this B meson, say its rest frame maybe, converting into energy that goes into the charm quark, the charm hadron, and into the leptonic system. So there's just a momentum conservation in the problem. It's natural to call the momentum of this combined pair, which is the momentum of the W boson, something. So let's call that Q mu. And then the momentum conservation would just like, at the hadronic level, be something like this. This is just a way of writing PB, the total momentum, and P of the D. So the momentum of the B is equal to the momentum of the D plus the momentum that goes into the leptons, which is Q. That's just hadronic momentum conservation. But you see that I can do the following. I can say, oh, well, this is, if I look at this another way, and if I square that equation, I get a formula for V dot V prime. So square, V squared and V prime squared are both 1. So that was a condition on our 4 vectors. And so when I use that and I solve, I get this for V dot V prime, and it's not equal to 1. It's greater than 1. It goes about between 1 and 1.5, depending on the value of Q squared. So I can go from a small Q squared, where there's very little energy, essentially no energy taken away by the leptons, to a maximum energy, where the B meson just changes into a D meson. Kind of the D meson is basically at rest, and all the momentum goes through to the leptons. So there's some kinematic range for this variable, and it's between about 1 and 1.5, roughly. But it's not equal to 1. So I really do need a different V and a different V prime to describe this process. And that's fine. Our theory is smart enough to have been set up with the option of having different V's and V primes. All right. So I'm going to eventually want to do matching for this between these two theories. This is a kind of matching. It's sort of like a complete, but this is kind of bottom up, right? I'm just thinking, like, what could the possible operators be? And I wrote down all the possibilities. I want to think about it also from the top down, do some calculations, and show you how the matching would work. So the matching is going to be some formula like this, where the QCD current, let's take the first case. Well, it doesn't matter, actually, if I make these into matrices, but it's going to be some formula for each of the currents, and maybe there can be some mixing as well in general. But basically, it's going to be some relation where the renormalized current in QCD gets matched onto the renormalized current in HQET, and there's some coefficients in front. Okay, and in general, there could be some basis of coefficients here, because there's a basis of operators, right? So there's some sum over elements of the basis, I. And then that's the leading order term, and then there's going to be plus order 1 over m, which we're not going to worry about. So this is just a leading order matching. So far, these C's have been 1. I just sort of wrote these things down. There was no C in front. Okay, at lowest order, actually, we're only going to match onto the first one, but we'll talk about that. Now, before we talk about, so I want to show you how to calculate these C's. Before we do that, I need to tell you how to do the renormalization, right? Because what I have to compare to do this matching is renormalized S matrix elements of these currents. So we'll spend some time renormalizing HQET, and then that'll lead us to thinking about anomalous dimensions in HQET. So we'll get examples of how large logs get resummed, and then we'll be able to come back after it's renormalized and use this formula for the matching. That's where we're going. Okay, so let's renormalize this theory. Well, we're normalizing it at one loop, which is what I'm capable of on the chalkboard. Requires calculating various loop diagrams. And I'm going to only calculate one of them very explicitly, and then I'm going to allow your imagination to fill in the gaps for all the other ones, because otherwise it would take too long. So we'll spend some time on the wave function renormalization, which is sort of the simplest thing, but it's a good place to start. So this QV field has a bare version and a renormalized version, and some z factor relates the bare and renormalized fields. So let's work out what the ZH is. Okay, so at one loop, the diagram that contributes to that is this diagram. We have some external momenta, we have some loop involving a gluon, which will let have momentum q. So internally this is p plus q, and then it goes back to p. And this is going to lead to a divergence that has to go into wave function renormalization. So let me calculate this. We will calculate it using, we'll make some choices. We'll use ms bar to define the z. That's our renormalization scheme. And we're going to use Feynman gauge to do the calculation, because that's the easiest for the gluon. So we fix the gluon in Feynman gauge, G mu nu type propagator. There's some prefactors. There's an I squared from this vertex. There's two couplings. There's a color factor. This color factor comes from the TA, but TA is just giving CF, the Casimir, which is 4/3 in QCD. This is not my focus, so I just wrote it down for you. But this is coming from the TA in the diagram. My focus is more on this loop integral. So we have an integral over the loop momenta Q. Just to be very explicit, the two HQET vertices are V, and then there's a propagator, which was G mu nu in Feynman gauge. So this is very simple. It's just V squared, and that's 1. There's a Q squared, that's the propagator of the gluon, and then there's the propagator of the heavy quark, and that's not, P slash plus Q slash. Now it's V dot P plus Q. Because P plus Q is the momentum going through that heavy quark. And there's plus I zeros that I'm not writing. In the MS bar scheme, there's another little factor that you stick in here, which I can put in for completeness. There's an e to the epsilon Euler gamma, and there's a 4 pi to the minus epsilon. That's the difference between MS bar and MS. MS bar removes these pesky numerical factors in its definition of mu. So let's be complete and stick that factor in there already from the get-go. So I just have to do this loop integral. I should keep the v dot p because in the end I'm looking for something actually proportional to the lowest order equation of motion, which is that v is v dot p. So I shouldn't set v dot p to 0. I have to combine the denominators here in the usual way, and then I can do the loop integral. Now, the usual thing you might think of is, oh, I know how to combine denominators. That's very easy. I have a Feynman parameter x, goes from 0 to 1. I'm going to get x times this and 1 minus x times that. That actually is not the easiest way to do this integral. The reason that's nice usually is that you have relativistic propagators in the denominator, and they're quadratic in q. This would have a q squared. This would also have a q squared. The second term is not quadratic in q. It's linear in q. And that leads to a little bit of a complication, because usually what happens is you multiply this by x, this by 1 minus x, and the q squared term, you get x plus 1 minus x is just 1. So there's no x in the q squared term when you combine the denominators usually. Here, if I just used x, that wouldn't be the case because there's no q squared term here. If I multiplied this by x, it'd be the only term that has a q squared, and it would get an x, and then I have to pull out the x. It's a little more complicated. So we use a different trick. Instead of using the usual trick, we could use the following trick, which is slightly nicer. We use a trick where we have what's this Feynman type parameter lambda, and we use this trick to combine the denominators. And the nice thing there is we can choose this lambda to only multiply, say, the v dot p plus q term, and the a will be the q squared term, and then we don't have the Feynman parameter multiplying the q squared term. So okay, so then we combine the denominators, and we get something with a combined denominator that looks like this. I'll put the I0 back in for completeness. So this would be the new denominator. And then we do the usual thing of completing the square. So I want to write this as some vector squared minus something, and then it's all squared. So I'm defining t, I'm changing variable from q to t, and you can quickly see that what I need to do, whoops, is I need to change variable to t, which is q plus lambda v, right? And then t squared will get this term right and this term right, so it's absorbing all the q dependence into the t. Of course, it induces the square term, but that I can just stick into this a. And then I can look at and figure out what the a needs to be to complete the square. And that's what it is. So it's the same kind of procedure that you always go through to do loop type calculations in a quantum field theory. It's just that we had this lambda that was more convenient than something like x. And there, you know, this is generalizing to other calculations in a theory with linear propagators. You could always do this. Okay, so I promised I would do some hard work, so let's do some hard work. So then I have some integral, there's no numerator, so I just have d dt over something that's t squared minus a squared minus a all squared. So it's a very classic integral that I can look up, you know, in some table. So I could just get the answer immediately at that point. So gamma of 2 minus d over 2. I'll write what I just said. There's a Feynman parameter integral. There's probably some mu to the 2 epsilon that I missed in my notes. And that's from just doing the knowing what the integral of d dt over t squared minus a all squared is. Okay? I could do this lambda integral. Mathematica knows how to do it. It remembers the formula better than I do. I can switch to my epsilon in order to see where the epsilon poles are. Let me do that for the place where the epsilon poles are. They're coming from this gamma function. There's some other gamma functions, but they're, as d goes to 4, just numbers. So they have an expansion. Mathematica knows how to do that too. And then there's a kinematic factor that comes from the dimensions of the integral, and that's minus. I pulled out some 2's. It's minus v dot p minus I0 to the d minus 3. The dimensions of the integral that we started with were 1, so we had to get something when d goes to 4 to be 1, and there it's the only dimensional thing in the integral is v dot p, so that's why it's proportional to that. Now I want the MS bar scheme renormalization, so I can expand this, and I just really lead to the 1 over epsilon pole. So I can expand, and I have a 1 over epsilon pole that looks like that. And then the way I want to think about it is there's some counter term. The counter term comes from the fact that there's this ZH when I switch to the renormalized fields. And so there's a Feynman rule that for something like this, okay, there's two Q's, so there's no factor of 2 in this. And it's just, as a Feynman rule, this. And to renormalize the theory, I just say, oh, the original loop diagram plus this counter term diagram are adding up to be finite, right? And that defines how the ZH should be. And in MS bar, the only thing I need is this 1 over epsilon. That's my definition of the, with the Z in the MS bar scheme. So I pick ZH to be 1, CF alpha S over 2 pi epsilon in MS bar. Then it's finite. Okay, so that's how the renormalization procedure works. You can look at the answer and you say, if I remember something from Peskin, or if I look up in Peskin and I thought maybe I could just take the answer in full QCD and get this answer, they differ. This is not the same as wave function renormalization in the Feynman gauge and for a full QCD quark Z psi. It's ZH and it gives you a different answer. Of course, the loop diagram is different, so maybe we're not surprised. But this is an example of seeing that the UV physics is different between the effective theory and the full theory. All right, well, that's the only loop I'm going to do explicitly for you, but it gives you an impression that you could do other loops. So now let's talk about what else we have to do. And let's focus on this case of B to U E nu first. So let's think through, if I want to renormalize the operators here, I have some C bare and I have some J HQET that's bare, and I need to switch that to a renormalized coefficient. So I would switch to a normalized coefficient. I'm going to write all the Z factors in front. I would switch, and I want to switch also to renormalized fields. There was various choices of gamma. So this gamma would be the gamma mu or the V mu. Okay, I'm just using a shorthand, gamma. It'll be simpler. So these Q's here, which I don't have any bare on them, they're the renormalized ones. In this here, on the left-hand side, I have bare fields. And so when I switch, I have a Z factor for the coefficient. I'll call that ZC. And I have a Z factor for each of the fields. So there's a ZQ to the 1/2 and a ZH to the 1/2. Okay, the ZH is just what we were talking about over here. So I have a QV on the left, which is bare, and I switch it to QV on the right, and there's a ZH. The 1/2, I have to do something similar for the light quark. I call that ZQ. So there's a product of 3 Z's. I've calculated for you this one. This one is the same as a full QCD calculation. So this one you can look up in Peskin. And then you need to calculate the ZC. So the usual way of thinking about this is to write it as something that's the renormalized operator plus a counter term. So we do that. So we treat this as a counter term. The second part. We do perturbation theory in it. The Z's are always 1 plus something. So like this up here, they're just going to generate some counter term Feynman rules. Okay, so how does the calculation look? We have these counter terms. We have a loop diagram that we haven't calculated. And that's a vertex type diagram. So in the effective theory, we have this heavy quark, which I'm denoting by a double line. We have a light quark, and we can have a loop diagram with a gluon between them. So that's a vertex type diagram that we need to compute. And then we have these counter terms, which conveniently can be written as z's minus 1. That's sort of the order alpha piece. So the wave function terms multiply the operator taken at tree level. They themselves are order alpha. This is order alpha. And then we have the counter term we want to determine, which is the zc minus 1. We don't know that. And we just demand that this is finite. And in the MS bar scheme, again, we just take this zc to be something of order 1 plus epsilon, or 1 over epsilon. It's just the 1 over epsilon term. So it's again the same procedure. We have to remove the wave function renormalization from this diagram in order to get off the zc. Okay, but these terms we know. Let's say we calculated zh, we can look up zq, and now we can just do this calculation. This calculation is going to involve an integral ddq. Okay, there's some q going around this loop. There's some numerator. It's linear in q from the q slash from this propagator. And there's some denominator. There'll be a q squared from the gluon. There'll be some v dot p plus q type thing. In this case, I can actually take this just to be v dot q, set the external momentum to be 0. I don't need to keep it. V dot p of the external particle here is 0 on shell. And then I have sort of the light quark. Okay, let me keep it in. Let me just say p heavy, q plus p light. So this is p heavy, this is p light. P light I just call p. There'd be a loop diagram like that. And v dot ph I could set to 0, p squared I could set to 0. Those are equations of motion relations. I'd have to do this integral. It's not that much harder than what we've done. You could combine these two with an x parameter and then the rest with a lambda parameter, or you could combine these first with the lambda parameter I told you and then combine things with an x parameter after that. You could do it, but I'll leave it to you. Yeah, good. So I dropped it, you're right. I should have written it. Thanks. Okay. Like this. So this one here we calculated, that's here. This CQ here we get from a QCD calculation of the exact sort of what we just did, or we'd look it up in Peskin or some other quantum field theory book where it's done. So this is wave function normalization. Because it's for the light quarks and the QCD Lagrangian is the same in HQET for the light quarks as in full QCD. That's why this calculation is the same. It's all the same Feynman rules. So we know this first line. We don't know the ZH. This is the thing that's unknown. This is the thing we're after. And we determine it by demanding that the sum of the diagrams is finite, the sum of these pieces. So we have to do this calculation. There'll be a 1 over epsilon divergence in this calculation. We have 1 over epsilon divergences here. And then we add everything up and we get ZC. And when the dust settles, some simple thing. In MS bar. Okay, well this ZC allows us to go back to that renormalization group equation that I wrote and to calculate an anomalous dimension for the coefficient. So let me explain to you how that works. So what was the formula? Yeah, there's one more comment that I should make. There was a choice here of gamma mu versus v mu. And you could say, well, don't you have to do this whole procedure at the top of the board there for both, right? For there's more than one operator, so in principle I should be renormalizing both. It turns out that the ZC is the same for both operators. So it's actually independent of the choice of the gamma. There's enough symmetry in the problem that you don't have to renormalize the operators separately. They have a common renormalization, and that's a combination of the heavy quark symmetry and the chiral symmetry of the light quark. There's enough sort of spin symmetry in the system, if you like, to make sure that it doesn't matter which operator. You get the same ZC. So it's the same ZC for both operators. So I'm just going to talk about it as if it's one thing, but it's true for both. Okay, so what is gamma? Our formula for gamma was the following. ZC inverse with a minus sign in front, mu d by d mu of ZC. So I need to calculate that. Okay, so you look over here and you say, well, one doesn't depend on mu. The second term depends on mu because the alpha is the renormalized alpha, and it depends on mu. Remember, we switched to the renormalized alpha. That's where the mu to the 2 epsilon came from. Okay. And if you say, I know the beta function for alpha, it's just like minus beta naught, maybe a 2 pi, alpha squared of mu. If I were to use that part of the formula, this 1 over epsilon would just be still hanging out. So I must be missing something if I'm just thinking about replacing it by beta naught alpha squared. So you have to be a little bit careful. So we look back and we remember that the bare coupling is the renormalized coupling, mu to the 2 epsilon. Okay, there's this pesky factor that we could keep if we want to be completely accurate. And then there's some renormalization constant z alpha for the coupling. That's the complete change of variable to the ms bar coupling. And so if I take mu d by d mu of the left-hand side, it's 0. And that's going to give me something on the right that's like mu d by d mu, alpha s, stuff. But there's also this mu to the 2 epsilon. And when I differentiate that, I'm going to get a 2 epsilon, and then mu to the 2 epsilon back, and then stuff. And then eventually I'm going to get stuff, and I'm going to get sort of mu d by d mu of z alpha. So there's a bunch of terms in this formula. And the one that we usually drop is this one. And the reason that we drop it is it's proportional to epsilon. And that's because we've done the expansion. We've gone to epsilon equals 0. But we can only do that at the very end. And now we need to keep it. So when we rearrange this formula, it looks like mu d by d mu, before we send epsilon to 0, minus 2 epsilon alpha. And then, okay, then there's the term that comes from the z alpha here, which is the one you're more familiar with in higher orders and terms from there as well, where this beta naught is the 11 or 11/3 Ca minus 2/3 NF, Ca being a 3 in QCD, NF being the number of light flavors, light quarks. So there's this term. And this is the leading term in alpha. It's the term we want to keep for the one loop anomalous dimension. We don't need to keep this. This is second order in alpha. We need to keep it if we're going to higher orders, but we're only working to one loop. So we need this first term. And so when we differentiate the z, it's this term that's going to matter. All right, so gamma. Well, the minus z inverse, we can just write 1 there. So this is just minus 1. And then we have mu d by d mu. And we just plug in zc. As I said, the 1 doesn't matter. We have alpha over 2 pi epsilon. And then for differentiating this alpha, we get a minus 2 epsilon. That cancels the 2 epsilon in the denominator. Now we're very happy. Okay, so that anything we're dropping here is alpha squared, so we're just working to lowest order in alpha. So there's 3 minus signs. So 1 overall minus sign. Okay. The fact that it came out to be finite maybe shouldn't be too surprising because it's a renormalization group equation for something that we define to be finite. C renormalized of mu is a finite thing, and it's equal to gamma times C renormalized of mu, which is a finite thing. So how could gamma depend on epsilon? It better not, or else something's wrong in my whole formalism, right? And yeah, it's not good. Things are working. So this is the anomalous dimension at one loop for this operator. And it's, pretty simple. As promised, I said, well, we could just get alpha times the number. The number is minus 1 over pi. A rather simple number. Let me talk a little bit about the physics of what that formula tells us. So remember our picture. We have QCD up here. We have heavy quark effective theory down here. And we might want to run to some scale that's lower than the mass of the heavy quark. So mass of the heavy quark is up there. We want to sort of evolve the theory below the mass of the heavy quark. And so the way that you should think about this formula, we have mu d by d mu of C, which I'm getting tired of writing C renormalized. If it's a function of mu, it better be the renormalized thing. So I'll drop the renormalized. So we have this differential equation for the renormalized coupling. It's a differential equation. It needs a boundary condition. That boundary condition is something that we're going to get from matching up here. We're going to get some at some scale, what I could call mu q. So let's say it's mu q, so order mq, maybe it's equal to mq. Doesn't have to be exactly equal. We're going to get from matching some kind of formula that looks like this. We haven't done the matching yet, but that's what we're going to get. And we're going to do that at some scale up here. And then we can do renormalization group evolution with this gamma, solve the differential equation with this boundary condition to get the coefficient down at any other scale. Okay, so that's the picture again. So far we've calculated the gamma, but we haven't calculated the boundary condition. All right, well, let me think of, I'll just write the boundary condition as if it's this. We'll keep it arbitrary, we'll fill it in later. And we'll think about like what level do we need to fill it in later. Let's just solve the differential equation and just see what the solution looks like. So, this is a pretty easy differential equation. I can write it as log C, derivative of log C, and derivative of log C is just gamma. I move the C from the right to the left. Okay, that's just minus alpha over pi. So solving the differential equation for log C, I just integrate left and right. I get log C of mu over C of mu q, if that's my boundary condition, is equal to minus an integral from mu q to mu, some dummy variable d mu prime over mu prime of this formula with the minus sign up front. That still looks like it might be a little bit hard, but we should make things as easy as possible. The reason it's a little bit hard is just because this is a function of alpha, and the variable here is that. At this point, we can use the equation in its finite form for the renormalization group. This is the thing that's governing the finite coupling. After the epsilons cancel, I send epsilon to 0. So we have this equation. And so if you like what we have is a coupled set of differential equations, where sort of this one is telling us what to put in here, and then we want to integrate in mu prime. But these are a very simple set of coupled differential equations, and the way that we can think about is just use the second one as a variable substitution into the first one. And so that works like this. We write this equation as d mu prime over mu prime is minus 2 pi over beta naught d alpha of mu prime over alpha squared of mu prime. Just a rearrangement. Substitute that in, then it's a very simple integral. So this trick always is useful. So I'm changing variable to alpha inside the integral. There's a factor that comes out front from doing that. I guess this becomes plus. And then there's the alpha. Now I'm like very happy to integrate this function because it's sort of I changed variable to make it trivial to do that. So one of the alphas cancels. I have g alpha over alpha. That's log alpha. This pi cancels this pi. There's the answer. Okay, now I can take the exponent of both sides. And I get c of mu is equal to c of mu q. Let me write that down here. And taking the exponent, well, I can put this 2 over beta naught up there. So it's alpha of mu divided by alpha of mu q to the power of 2 over beta naught. That's the solution. So this thing here is the evolution kernel that takes us from mu q to mu, and it's just a ratio of couplings at the two different scales, raised to some power that came from the anomalous dimension. Okay. There's a beta naught in there as well. To see that this is summing logs, remember that alpha between one scale and another scale is given by some logs. And as far as this equation is concerned, we could stick in that solution that relates alpha at two different scales, and then we can see very explicitly that this is summing some infinite set of logarithms, and exactly what set of logarithms it's predicting. So sticking in that formula, we'd have the following. And I could do a series expansion here. And it would start as 1, and there'd be an alpha and some logarithm L, and then there'd be an alpha squared and some logarithm L squared, right, with some numbers in front. So it's an infinite series of logarithms that have been resummed by this procedure. And if this mu over mu q is large, it's a large logarithm, and we've summed it up. And that's nice. So what's happened, just in terms of the physics, is that we've figured out how to evolve from one scale to another scale. We've figured out, in terms of the original physics of the QCD, how to split some kind of logarithm that might have shown up that might have involved mq over lambda QCD into sort of a logarithm of mq over mu and a logarithm of mu over lambda QCD, some IR scale, where this is sort of going into the coefficients, this is going into the operators, and we have control over these logarithms because it's related to the renormalization in the effective theory. Even though, what the scale for the HQET might be lambda QCD, we're still sort of able to split because there's perturbative physics. We're able to split this logarithm and control it because the physics of the coefficient is perturbative. And we can control these logarithms and sum them. We wouldn't run all the way down to lambda QCD. We'd stop maybe at a GeV. But this is we talked about this before, other examples. In this example, the two scales are MQ and lambda QCD, but the paradigm goes through no problem. So the idea is that these logarithms are very easy to compute in the effective theory, because all you needed to do to compute them was find the 1 over epsilon, right? We didn't even need to keep the finite parts of the diagrams. It's very simple. The simplest part of the diagram is the divergence. Drop everything else, and we get these logarithms. Now, if we ask about the accuracy of the boundary condition here, it turns out that we don't even need the boundary condition to sum these logarithms. If you look at my boundary condition, it was 1 plus alpha, but in the boundary condition, there's no large logarithms. This L is a large logarithm. The boundary condition might have some small logarithms. It doesn't have any large logarithms. So I can actually just replace this by 1 at this order. I don't need the order alpha. And then this is all I got. So it really is just the 1 over epsilon. I don't even need to do the matching if I want just the leading logarithms. So for the leading logarithms, this is alpha log mu over mu q to any power. Those are the leading logarithms. K being a positive integer or 0. We can set the boundary condition to its tree level value, which is, we can say is 1 in this some units, or it would be 1 for the, technically only for the vector current, the gamma mu current. Okay, I'll say in a minute what happens when you go to higher orders. Let me see if there's any questions about what I just told you. All right, so I'm going to have some various comments. What are we going to learn from this? What can we extract from this that's more true more generally? In the end of the day, we have a Wilson coefficient and a current in the effective theory, which was HQET, but we'll just sort of extract a more general lesson. The current is some matrix element of an operator. It depended on mu. When I expanded the 1 over epsilon, blah, 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 in the diagrams, there was a log of mu, got left behind. That log of mu is defining the matrix element of the operator, at least perturbatively. And so the operator's renormalized operator depends on mu too. And so the Wilson coefficient depends on mu, the operator depends on mu. The full theory didn't know about this mu. The full theory is up there. This mu is down and is part of the definition of splitting the operators and coefficients in the effective field theory, not something about the full theory. So in the end, the mu dependence of the coefficient and the operator cancel. Okay, and so this mu is acting like a factorization scale where we have MQ up here, we have mu, and we kind of we can slide this scale around, and we have a matrix element of J that we might end up wanting to take the matrix element of the J down at some scale, maybe not lambda QCD, but maybe somewhere above lambda QCD, like 1 GeV. And this picture of factorization between the sort of short distance coefficient and the J and the fact that we have a sliding scale that we're able to choose at different values allows us to take this and do the following. We can write the coefficient at some scale that's high, mu q. There's some evolution factor, that's just this ratio of alphas that I talked about. Sometimes it's called u. Sometimes this would be denoted by c times u. And then there's the j at mu. And I can take this thing here to be like mu equals 1 GeV. And then when I take matrix elements of J, there's no large logs in those matrix elements because it's small scale. This, I take mu q to be of order q, mq, a high scale. There's no large logs in the c, and all the large logs are in the u. And so I've separated the physics at the two scales into sort of finite calculations. Maybe this is a non-perturbative calculation, but so what? This is a perturbative calculation. We'll do it momentarily. And then we have large logs that are connecting the two scales. So this is a general paradigm. And it's not specific to HQET. It's sort of how to interpret anomalous dimensions in the effective theory. And it's also how we think about running the coupling, right? When we run the coupling in QCD, we use a coupling associated to the physics of the scale we're looking at. So if we're doing B physics, it might be alpha S at MB. If we're doing some electroweak physics, it might be alpha S at MW or MC. It's the same paradigm. We're just calculating the renormalization in this effective theory for the coefficients of the operators in the effective theory. There's another sort of more subtle comment. You could say, well, we use the MS bar scheme. You know, how does that come in? When experimentalists make measurements, they don't have to tell you, okay, when experimentalists measure some observable like a cross-section, they don't say, oh, this cross-section's in the MS bar scheme. They just say, this is the numbers, right? So observables don't depend on your choice of scheme. What depends on the choice of scheme is splitting the physics between C and J. You decided, and I'm going to make a split. I had to define precisely what I meant by the mu, right? And that causes a split of the physics between C and J. This Wilson coefficient has a definite definition. This operator has a definite definition. It's got to be the same as the coefficient. So if I define this in the MS bar scheme, this also has to be in the MS bar scheme. And that cancels. The choice of scheme cancels between C and J. And that's why observables don't depend on the scheme. It's just our split between the two sides that depends on the scheme. That means you have to make the same choice for the two. MS bar here. Otherwise, the scheme dependence wouldn't cancel. And that can matter, because if I'm, for example, using some calculation of C in the MS bar scheme, I did perturbatively, and then my lattice friends calculate matrix elements of this, they have to convert their answer to the MS bar scheme if they want to put it back together with my result for C. So this is important to keep in mind. All right. Any questions about these comments? Yeah. 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 Yep. Yeah, I mean, there was a Q bar Q gauge field, but it was V dot A in that Q to V dot D. That was the only one. And that one's connected to the V dot partial, and that's the only one that's leading, right? And so you could say, well, in the rest frame, that's A0. What happened to the A vector, right? The A vector didn't couple to my heavy quark at leading power. At subleading power, if I get, depending on where we get to today, I may tell you what the subleading power looks like. Subleading power, definitely you couple to the A vector. And now you can ask, like, what are the Wilson coefficients of the operators at subleading power? They don't have to be fixed. It's because you can't use the same argument there. At the leading order, yeah. Go ahead. Yeah, yeah. Yeah. Yeah, so like the V did change from this kind of hitting it with the W boson, and I'll talk about that case momentarily. Yeah, so we'll see at least if I perturb V once and it changes, what happens momentarily. But in this example where it was B to U, it didn't change. The dynamics didn't change it. Okay, how would the things generalize to higher order? This is sort of my last comment. So we calculated this anomalous dimension, and it was an order alpha thing, but I dropped some order alpha squared term along the way, and you can just sort of imagine that if you were to do things at higher order, what would happen is that we had some coefficient times alpha over pi, coefficient was -1. If I kept going in the series, there'd be a coefficient of alpha squared, say over pi squared, etc. So this is the one loop anomalous dimension. This would be a two loop, what's called a two loop anomalous dimension. And then there would be a three loop anomalous dimension, etc. So the differential equation has a series expansion in alpha. The boundary condition, which we didn't calculate yet, it has a series expansion in alpha. And I can kind of denote it, whatever I get for that boundary condition, I can denote it also as a series in alpha over pi. I'll just call the coefficients A. So there's a series expansion in the boundary condition, a series expansion in the anomalous dimension. And we've just sort of kept the first term in each, and that was the leading logs. And then you can keep the second term in each, and that will be the next leading logs. So you can make a little table. LL is leading log. Anomalous dimension, I need it at one loop. Boundary condition, I need it at tree level. That was just the one. If I want to do next the leading log, then I would need this at two loops, and I would need this at one loop, etc. Next and next the leading log, three loop, two loop. This would sum the series that we talked about, which is alpha L to the any power. This would sum the series with one extra alpha, which is a different set of coefficients. And this would sum the series with two extra alphas. And so we can get more and more precise by including more and more terms, and we can sum more and more logarithms. If we want high precision, maybe we go to this order. But that's kind of the general paradigm of resum perturbation theory. So when you hear people say leading log, next leading log, next leading log, it's sort of like this is what it's about if they're single log series like this example. Okay, and you could solve those equations the same way we solved this one. It's actually not that much more hard to solve the equation with the higher order terms included. It's just a very fairly straightforward differential equation to solve. This was all for one example. Let's talk about the other one. We had two. The other was B to C E nu bar. We can go through the same procedure. C renormalized, C bar, J bar, write it out as an operator. Okay, there's C renormalized, which I won't forget this time. Now there's operators that had this form, QV, QV prime. This was BV, CV prime, but let me generalize it, call it QV, QV prime. And then there's a counter term. This time there's a wave function factor ZH, which is the same for the QV and QV prime. So this would be the formula for this case. Okay, it's very similar to the formula before. Instead of having root ZH, ZQ, we just have a ZH. And then the operator's a little bit different operator. And we'd have to do a different calculation, right, for the vertex diagram. we'd have to do this calculation in the heavy quark effective theory, where we have something along V and something along V prime. And so the loop integral that we would need to do here, okay, I guess I was calling the loop momenta Q, would be K squared for the gluon, and then we would have a V dot K and a V prime dot K for the two heavy quarks that are along the two different directions. So the vertex diagram has a different loop integral. And it may not surprise you that the answer can depend on V dot V prime. Why not? So actually the anomalous dimension depends on V dot V prime. So in this case, it's not a number. It's a function of V dot V prime. So when the dust settles on this calculation, the coefficient is 1, alpha s, there's this factor of 4/3, and there's a 2 pi epsilon, and then there's a function that sits here, which I can write like this, where this r is a function, which is a logarithm. Looks like logarithm of some variable w, square root of w squared minus 1 over square root of w squared minus 1, where w is the shorthand for v dot v prime. So the anomalous dimension is going to also be a function of v dot v prime. We can do the same thing we just did. And we have this omega r of omega minus 1 showing up in our anomalous dimension. So now it's a function. That's more interesting. You can check if I expand about 1, the logarithm vanishes, as does the denominator. You can actually check that r of 1 is equal to 1. So it's a well-behaved, it's not like it's blowing up anywhere, this function. And so over the boundary between the physical values of w that we were interested in the process I described to you, it's just a finite number, but it's a different number for each value of v dot v prime. So as I change the momentum transfer from the neutrinos, I have a different anomalous dimension in this case. So it's more non-trivial as a function, not just a number. Okay, so now it looks like it's encoding some more interesting information. I should also mention that it's independent of the choice of spin structure again. And that's because of the heavy quark symmetry, basically. This calculation of this loop diagram really doesn't care what you stick here. It's the same loop integral. So we have this universal anomalous dimension for the heavy quark effective theory operators that are making this transition from heavy to heavy. And the Wilson coefficients likewise are functions of W. If you think about dimensional analysis, you say, oh, well, what could the Wilson coefficients depend on? They could depend on mu, they could depend on alpha, they could depend on the things I'm integrating out, which are sort of MBV and M charm V prime. But MBV and M charm V prime, which are big things, those are the large momenta of the bottom quark and the charm quark, those are 4 vectors. The Wilson coefficient is a scalar, right? These things have indices, mu. And so if I write it in terms of scalar quantities, well, alpha is scalar, so that's already good. I could write it, the C is also dimensionless in my normalization, so I could write it in terms of dimensionless quantities that are scalar. Alpha counts. Mu doesn't count, it's got dimension. I could write mu squared over this squared. V squared is 1, so mu squared over mb squared, mu squared over mc squared, those could show up. But then there's also another dimensionless thing that could show up, which is v dot v prime. And so all those show up. Okay, so the Wilson coefficient can be a function of v dot v prime. Maybe it's not too surprising. Its anomalous dimension could also be a function of v dot v prime. And the way that you could think about why this is happening is as follows. You could say, well, after all, I'm renormalizing this operator. And from the point of view of the dynamics, the v and the v prime, they were just like indices, like I, j, 1, 2, 3, v, v prime. So I choose a v, I choose a v prime, and I get an answer. I choose a different v, I choose a different v prime, I get a different answer. Okay, so they're behaving like indices on the current effectively. Like some external indices, and the answer can depend on the dot product. They're 4 vectors. Okay. In the interest of time, I will go over to talking about the matching, which I promised. So the matching is kind of a generalization of what we've been talking about with the loop diagrams, where now I have to do the full theory calculation in the loops as well as the effective theory. And I'm just going to write, some generic structure of things. This is needed to get the perturbative corrections in the heavy quark mass as the scale in the alpha. Again, I'm going to use MS bar. I'm going to use Feynman gauge, but I'm not going to write enough down that you'll know that. So what I'm writing down would actually be true for any gauge. So we have to compare QCD, and we have to compare HQET, and we have to compare renormalized S matrix elements. We know how to renormalize QCD. We just learned how to renormalize HQET, so we're all good. So let's write down an S matrix element of, say, some light quark with spin S. And I'll do this for the heavy to light case. So let's do the case B to U, E nu bar, the simpler case. So in my QCD, I have some matrix element of a heavy to light transition with the heavy to light current, which I'm denoting as Q bar gamma mu Q. And because it's an S matrix element, there's some factors in front related to how I normalize the propagators in the theory. There's some thing called residues in the LSC formula. And then there would be some spinners. There would be some loop corrections, which I'll call V. So it looked like I could write the answer down in this form, where these things here are UV finite residues of propagators in my wave function normalization graphs. Okay, in the QCD, there's a diagram with heavy quark, diagram with light quark, and these R's are finite. You might say, like, when I did these calculations, I only kept the 1 over epsilon, that went into the Z, that was the MS bar definition. What about the finite terms? Do the finite terms matter? Yes. The finite terms from these diagrams go into the kind of residue in the propagator. So the propagator is like 1 over p slash at tree level, but then the loop corrections could give something instead of 1 in the numerator. That's the residue of the propagator, R over p slash. And it comes back, because when I do the LSZ, to define my S matrix elements, I have to sort of pull out how my propagators are normalized. In the MS bar scheme, I chose to have some non-trivial normalization for my propagators, because I only define my Z factor by the 1 over epsilon. Another way of doing the calculation would have been to force it to have residue 1, so like just 1 over p slash at all orders. That's a different scheme for the wave function renormalization. That's not MS bar. Then these R's would be 1, but the V would change. So this answer is independent of that choice, but like in the case of what I'm doing where it's MS bar, I have some finite residues, then I have to be careful about the use of the LSC. This V is coming from the loop diagram, but now the finite parts of the loop diagram, which is taking me from heavy quark to light quark. Okay, so that's what the QCD looks like. And the HQET looks very similar. Well, now I have a residue for the heavy quark and a residue for the light quark. So the residue for the heavy quark diagram is different. Residue for the light quark diagram is the same. I also have some spinors. My calculation of the EFT graphs is actually independent of gamma, so that makes the calculation here a little simpler. For the finite pieces, I can pull the gamma out of the V and the 1. It's the same in both. So I can write it this way, where this is the finite parts of this diagram, and these residues are the finite parts of the heavy quark loop as well as the light quark loop. So this is H, okay, Q, QV this time, and little q again. So this diagram here is the same as this one over here with the little light quark, but the capital Q1, capital QV1, they differ, just like the ZH differed. There was two operators, so when I go through the matching procedure, there's going to be two coefficients. I didn't give them names yet, so let me give them names so I can write some results. So there's C1 and C2. I put a V for vector. And by comparing these two calculations of these loop diagrams, I can calculate C1V and C2V. So let's look at C1V. Well, it's 1 at tree level. And then the calculation, if I compare these two sides, the RQ is the same. So that actually cancels when I subtract. If I expand RQ is 1 plus order alpha, it still cancels out between the two sides. But the R for the heavy quark don't cancel. So I have RQ minus RH. There's a half because of the square root. The 1 cancels here, but there'll be something order alpha that doesn't cancel. And then I have to compare the vertices, and I called the vertex over there V1, and I can call the sort of scalar component of it that I extract for this operator, I could call it V11 or something. Okay, my notation's not great, but so this combination, differences of the residues, differences of the vertex diagrams, is giving the matching coefficient. I'm just choosing this matching coefficient to fix the effective theory, which is the minus parts, to get back the full theory, which is the plus parts. And when I take these differences, any IR divergences cancel. It's just UV physics that's left in the differences, because the difference between the full and effective theory is UV physics. And so I plug in my results, and I get an answer which is log MQ over mu minus 4/3 for this. And so previously I said, take this to be mu q, so this would be mu q, this would be a mu q. I said take mu q of order mq. If mu q is of order mq, that's not a large log. Okay, so that's the presence of that log was sort of in the back of my mind why I was thinking that the matching should be done at a scale of order mq, because I don't want that to be a large log. I want all the large logs to be summed by the anomalous dimension and not be part of the matching. My boundary condition should be something that's order 1, kind of order 1 in a log sense. For C2V, things are in some sense easier, a little bit, though you have to think a little harder. Because there's no C2V at tree level. and I do the tree level calculation, it was just gamma mu in the full theory, right? So I get a gamma mu term. I don't get a v mu term. But when I do the loop diagrams, I do get a v mu term. And so this actually just comes from the full theory v. And you get some finite correction. You see the effective theory calculation, I'm going to have to multiply by the Wilson coefficient, right? And the Wilson coefficient was 0, so I don't get access to like the loop diagrams in the effective theory. But the full theory, there's the full theory. I do the vertex diagram. There is a term that goes like this, q bar v mu q from the full theory, and that predicts this answer. So it's an easier formula, but harder to understand because of the 0. And that's affecting sort of which terms survive. At higher order, the C2 would also rely on the loop diagrams in the effective theory, but this order doesn't. That's matching. These are the values that the coefficients need to take at order alpha. Now I could take these, along with some two-loop calculation of anomalous dimension. I could get the next leading logs. And I've fixed up my EFT to get the right UV physics. All right, so, or maybe stop in 5 minutes. I think there's been enough, I have kind of a choice of what I talk about. I think there's been enough interest in the subleading terms in HQET that I'll spend the 5 minutes briefly talking about those. So we can go to in HQET to higher orders in our power counting expansion. And it's a power counting expansion in 1 over the mass of the heavy quark. And we had a Lagrangian that was a version of QCD that was sort of set up in a nice fashion in order to do the expansion. And we could just do that expansion keeping subleading terms. So let me explain to you how you could do that. So remember, this was QCD, just written in funny variables. So we can take QCD, written in these funny variables, and we can integrate out the BV field. And I'm going to do that just for you at tree level. So at tree level, integrating out the BV field is like taking this Lagrangian and writing down an equation of motion for BV, which I can do by taking a functional derivative with respect to BV bar and setting that equal to 0. If I do that, I get I v dot d plus 2mq BV is equal, there's a minus sign here, I dt slash qv. So formally, I can just invert this operator. BV is equal, let me put the 2mq first, that's bigger, IV dot d minus 1 I dt slash qv. That's the solution of the equation of motion for BV. And I could think of this thing as an infinite series where the 2m is big and the IV dot d is small, because remember, derivatives acting on qv are small. So that's formally how I can think about this formula. And you see at lowest order it's 1 over m. That was our neglect of it. But now we could keep the subleading terms in its expansion and see what we get. Okay, so formally, if I plug that back in without expanding, let me do that. I can write the answer like this. You see 2 of the terms here with the BV bar, this term and this term, I used to get this formula. So when I plug it back in, these terms cancel, but this term doesn't. The BV goes into that term and it generates what I wrote over here, this. And now I can expand. Well, expand just means sort of drop that. at lowest order, that's just set to 0. And then I get a subleading term for HQET. So I just keep the subleading terms from this, and it's, okay, there's two i's, so I can write that as a minus sign. Two d perp slashes. And then there would be higher order terms, so that would be L2, etc. At tree level, this is the way you can think about having done the matching. Now, notice that MQ here, the fact that there's the mass of the heavy quark means that if I put bottom or charm, this is breaking the flavor symmetry. It matters whether it's M charm or MB at this point. And the D slashes, which are gamma matrices, break the spin symmetry. So the symmetries get broken at this point. And this operator tells you how they're broken. Now, it's convenient to do a little bit of algebra on the D's. And this is not how it's usually written. The reason is that you can write it sort of as a symmetric and antisymmetric combinations of the gamma matrices. And that's kind of more convenient. So here's an identity. I could write it as anti-commutator of the gammas dotted into two D's plus commutator of the gammas dotted into two D's. And this is actually a little nicer way of writing things. Anti-commutator is just G mu nu, the 2 cancels, so this is just dt squared. And the commutator is like what we usually call sigma, and this anti-symmetrizes the D's, which gives it G mu nu. So this second term can be written as G over 2 sigma mu nu G mu nu. So this is usually how we simplify things. And then we have two operators instead of just the one. And this is nice because this is like a better basis when you go to higher orders. These things don't stick together, and they're no longer friends at higher orders. And so the usual HQET Lagrangian is written minus QV dt squared QV over 2MQ, and then minus G QV sigma mu nu G mu nu QV over 4MQ. And this is a kinetic energy term. It's like a correction from the motion of the heavy quark, made gauge invariant. And this one is called a mag moment or chromomagnetic moment. I'll just call it magnetic moment. The first term actually doesn't break the spin symmetry because the slashes went away. It only breaks the flavor. The second term breaks both. So now the way the symmetry is broken is a little different. So this breaks flavor. From the 1 over MQ, this breaks both. But it breaks it in a very particular way given by this operator, so there's still actually some predictions. I don't have time to cover all that. The matrix elements of these operators are non-perturbative parameters, and I already mentioned to you one of them long ago, which was lambda 1, and it was related to the matrix element of this operator. So some heavy quark state. And there's some lambda 2 that's a matrix element of this operator. Okay, so these are where can encode the power corrections into universal matrix elements. And what do I know? I know from dimensional analysis that this is some number that's of order lambda QCD squared, but it's some particular number that I can use and make predictions in terms of fit from one place and use in other places. So the theory remains predictive at subleading order because things get described in terms of a small subset, of kind of non-perturbative parameters that are correcting for the dynamics, in this case encoding something about kinetic energy that the non-perturbative gluons shift the heavy quarks by, and a chromate and a spin flipping term. Anyway, I think that's kind of nice. And I'll say one more thing and then I stop. It turns out that there's enough symmetry to fix the Wilson coefficient of this term such that it doesn't change from 1. Kind of non-trivial. But this term gets a non-trivial Wilson coefficient. So this would have some Wilson coefficient, C magnetic. And this one actually has a Wilson coefficient that in most reasonable schemes is fixed to 1. So the kinetic energy actually doesn't get changed. But the chromomagnetic term has a non-trivial Wilson coefficient. It's been calculated to 3-loop order. This C magnetic. This one's 1. And that's related to this reparameterization symmetry I told you about. It actually connects the leading order kinetic term to this operator, but not to this operator. Okay. I'm done. Happy to take questions. Yep. Yep. Yeah. So what happens, so at higher orders, when you do the reparameterization symmetry, this operator never gets connected to the IV.D term. And that's why it can have a non-trivial coefficient. But I could go to higher orders in this expansion. 1 over m squared, 1 over m cubed. People have actually done that. And then it turns out that when I make the reparameterization transformation on this term, it gets connected to some of those higher order terms who have to have this coefficient. So it's like the infinite